We should begin with thermal concepts.
Thermal interactions are a concept in physics in which the direction of energy transfer goes from a high temperature to a lower temperature until the objects reach the same temperature, which is known as thermal equilibrium. There are three main ways in which thermal interactions are able to transfer energy. These are conduction, where energy is transferred through objects by particle-to-particle collisions; convection, where energy is transferred through the distribution of fluids, which are gases or liquids; or radiation, where energy is transferred through electromagnetic radiation that is emitted from a body.
Temperature. We usually take temperature as the measurement of how cold or hot is something, but defining temperature this way wouldn't be quite correct. In the physics context, we define temperature as the measure of the average random kinetic energy of the molecules. Not to confuse with heat, which refers to the mechanism of transfer or energy in a thermal interaction as a consequence of the difference in temperature between two bodies. But now, what does the definition mentioned before of temperature refer to? Basically, it's measuring only the average kinetic energy generated by its particles by vibrating and/or moving around randomly, but not including any external input in the measurements, such as throwing the object around or manipulating it physically, as it increases the kinetic energy of all of the particles in what's called order macroscopic motion. Finally, temperature is directly proportional to the average random kinetic energy of its particles, when it's in Celsius or Kelvin.
We are all accustomed to measuring temperature by using Celsius or Fahrenheit scale as they are convenient, but in this case it is important to know and understand another scale called Kelvin, which is demonstrated by the letter K. For those familiar to the Celsius scale, it is very simple to do the conversion to Kelvin. All you have to do is T, the temperature in Kelvin, is equal to the temperature in degrees Celsius plus 273, and the Celsius scale can only go to a minimum value of 273, therefore K only can have a value of 0 or greater, which means it will never have a negative value. An important thing to notice is that it is noticeable that the temperature in Kelvin is actually proportional to the average random kinetic energy.
Internal energy. The internal energy is the sum of the total random kinetic energy and the total intermolecular potential energy of its particles. The internal energy differs from temperature by not measuring only the average random kinetic energy, but also the potential energy between the molecules. This means the energy of the molecules by being in the present state. Likewise, this intermolecular potential energy is highly related to the state of matter of the object, which we will later relation while talking about latent heat. Finally, internal energy is not to be confused with heat, as heat is a process, while internal energy is a quantity.
Specific heat capacity is the amount of energy that is needed to change the temperature of a unit mass of a substance by 1 Kelvin. Therefore, the higher specific heat capacity, the harder to cause that change in temperature, and vice versa. The specific heat capacity is determined by the equation Q equals mc delta T, so if you rearrange it, then you will get that C equals Q over m delta T, with specific heat capacity having the units of joules per kilogram. Some of the factors that specific heat capacity depend on is the mass of the object, so the bigger the mass is, the easier it is to heat, as well as what substances the object is made out of, as they might have different specific heat capacities.
Heat capacity. As not everything is composed of one type of molecule, we have to consider heat capacity. The formula is heat capacity is equal to total energy over difference in temperature. Heat capacity is the energy required to change the object's temperature by 1 Kelvin, but only reference to the temperature of that object. It differentiates from specific heat capacity because instead of considering the object is made of only one material, here we consider it may be composed of any mixture.
The changing of phase is something that occurs when a particular substance reaches a point in it which the molecules in it start to break forces or create forces of attraction between its bonds. When this change in phase occurs, the substance remains at a constant temperature until it is completely finished the process. There are 6 different phase changes in which that are possible within solids, liquids, and gases. So first is melting, which is from a solid to a liquid and breaks the forces of attraction. Then freezing from a liquid to a solid, which increases the forces of attraction. Evaporation, also known as vaporization or boiling, which is from a liquid to a gas and breaks the forces of attraction. Condensation, from a gas to a liquid, which increases forces of attraction. Sublimation, from a solid to gas directly without passing through the liquid phase, breaking forces of attraction. Deposition or desublimation, which is from a gas to a solid directly without passing through the liquid phase, increasing the forces of attraction. Energy exchange during a phase change only involves the intermolecular potential energy of the substance. This means the internal energy would be affected in one way or another, increasing if bonds are broken and decreasing if bonds are created. In order to change phase, a substance requires a specific amount of energy to do so, or more, in order for that to occur, because each substance also has its own unique potential energy. This is where latent heat comes into the picture, since when energy is released or absorbed per unit mass of an object during the phase change at a constant temperature, this is called latent heat. Because the interatomic distances vary between substances and phase changes, the amount of potential energy required is different, and we can classify them into 2 different categories, which are latent heat of fusion for the phase change between solid and liquid, and latent heat of vaporization for the phase change between liquid and gas, represented by L sub F and L sub V respectively. It is possible to calculate the latent heat of fusion and vaporization with the usage of this formula: Q equals ml, so therefore L equals Q over m, with the units being J per kilogram for L, which is latent heat. An important observation to make is that the latent heat of vaporization is significantly greater than that of the vaporization, meaning it does not take as much energy to change from the solid to the liquid phase as the liquid to the gas phase. This is due to the interatomic separation between the phases, making it easier to separate as they are already partially separated in the liquid.
Graph analysis. Now, all of the information, or at least most of it, viewed before, it could be recollected in this simple temperature time graph. Here we observe a heating process. To simplify the explanation, we will interpret it as if we were dealing with ice. In point number 1, we evidence the heating process of the ice to reach its melting point, which in point number 2 stays in the same temperature due to the energy being consumed in the intermolecular bonds of the object. By separating these bonds to convert the solid to liquid, then in point number 3, the liquid increases its kinetic energy proportionally to the temperature until reaching its boiling point, in which at point number 4 consumes enough energy according to its latent heat to convert all of the mass of water into gas, in which finally at point number 5 it may continue increasing. Likewise, in the other image already labeled, we may observe the inverse process from gas to solid, in which it first goes through condensation and then freezing. Now we may follow with thermodynamics. Internal energy of an ideal gas. We've seen internal energy before, but there's quite some differences with internal energy of an ideal gas that need to be highlighted, as this corresponds to an ideal gas and they exert forces only during collisions. There's only kinetic energy in the internal energy of an ideal gas, resulting in the following equation for the average kinetic energy of an ideal gas. So, internal energy is equal to 3/2 times number of moles times ideal gas constant times temperature. So, it may also be seen as internal energy is equal to number of molecules times Boltzmann constant times temperature.
Work done is related to the amount of energy that it takes to move a certain distance. A formula that you may have seen before to calculate work is W equals F times S, which is work equals force times displacement. Let's say that a gas inside of a container with a frictionless piston and the gas all of a sudden moves the piston outwards and does some work. How are you able to calculate this? Well, using the formula work equals the force times the change in displacement, we know that the force is pressure times area, from pressure equals force upon area. So we get W equals pressure times area times the change in displacement. And since the change in volume equals to the pressure times the change in displacement, we can end up with work equals to pressure times the change in volume. However, it is important to understand keywords of terminology. So if work is done by the gas, it is given a positive sign, and on the gas is a negative sign.
Laws of thermodynamics.
The first law in thermodynamics is not actually called the first law, but the 0th law. The reason for this is because it was established after the other laws of thermodynamics and is more fundamental, so then they decided to provide it with a lower number, so it is 0. The main concept of the 0th law of thermodynamics is that if two thermodynamic systems are in equilibrium with the third one, both of those two systems are also in thermal equilibrium. This can be expressed mathematically as A equals B, B equals C, so therefore C must equal to A.
The first law of thermodynamics. The first law consists of basically the law of conservation of energy applied to a thermodynamic system. But from here, it's observed the different systems and the surroundings affecting the system. First, we will define the surroundings as the external region with the system with which it interacts. And now, we may continue with the three types of systems. The first one is called an isolated system, in which no thermal energy, work, or matter is exchanged with the surrounding. An example will be a thermos. Next, we have the open system, which is opposite to the isolated system, as thermal energy, work, and matter can be exchanged with the surroundings. An example would be a boiling water in a pot without a lid. Finally, the closed system, where thermal energy and or work can be exchanged with the surroundings, but no matter. An example would be boiling water in a pot with a lid. And taking these systems in account, we can observe the four possible thermodynamics processes. Beginning with the isobaric process, in this type pressure stays the same, but volume may increase or decrease. To calculate the heat in this type of process, we use the formula heat is equal to change in temperature plus work. Meanwhile, for finding the work, we simply find the area of the shape in the volume pressure graph, with work is equal to pressure times change in volume. We may also use the relation volume 1 over temperature 1 is equal to volume 2 over temperature 2. And in a pressure volume graph, this process would look as shown. Then we've got the isothermal process, in which the expansion and compression of the gas is done slowly to maintain a rate in which the temperature remains constant. As it remains with constant temperature, it also has constant average kinetic energy, causing the heat formula to be simply equal to work. So heat is equal to work. The work formula would also be to calculate the area below the line in the pressure volume graph. And this process has the relation pressure 1 times volume 1 is equal to pressure 2 volume 2. And in a pressure volume graph, it will look as shown in the image. Following up with the adiabatic process, in here the process occurs rapidly, so the thermal energy is not transferred with the surroundings. The heat formula would correspond to heat is equal to change in internal energy plus work. Work will also be calculated by finding the area below the line in the pressure volume graph. And this process has the relationship of pressure 1 times volume 1 is equal to pressure 2 times volume 2. Also, in the pressure volume graph, the process would look as shown. Also, it should be mentioned that in an adiabatic process of an ideal monatomic gas, this constant should be considered. So pressure times volume to the power of 5/3 is constant. Finishing with the isobolometric process, this process is the one in which pressure may increase or decrease, but the volume stays the same, for which the heat is equivalent to the change in internal energy, as it has no work. It has also the relation of pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. And in a pressure volume graph, it would look as shown in the presentation.
The idea of the second law of thermodynamics is that if the temperature of a substance is increased, then the average kinetic energy of the system also increases. This results in some disorder in the system. Usually, the larger the volume of the substance, the higher the disorder of the system is, or can be. We call this disorder in the system as entropy, represented with the symbol of S. It is defined in the equation as the change of entropy is equal to the change in thermal energy over the temperature. Remember that temperature should be Kelvin. If not, you can make the conversion as I mentioned previously. In this equation, entropy has the unit of joules per Kelvin. It is important that the temperature is constant in order for the calculation to work, otherwise calculus will be needed to do the calculation. A basic concept that should be identified in this sort of calculation is that if you add heat to the system, then both the values of the change in entropy and the change of thermal energy are positive, and if heat is removed, then both of them will be negative. This law can be seen from two different perspectives. It is mentioning entropy changes within an isolated system, but another interpretation is that the thermodynamic process is irreversible. Because of this, the entropy in the system must always increase, and once all the processes are complete, and since they're irreversible, this will cause the thermal equilibrium or maximum entropy, and this results in what is called the heat death of the universe. There have been several statements formulated by famous scientists to try to help comprehend and make sense of the second law of thermodynamics. First is the Planck statement, which says, in an irreversible process, the total entropy of an isolated system increases. In a reversible process, the total entropy of a process remains unchanged. Next, the Clausius statement, which says thermal energy cannot be spontaneously transferred from a cold to a hot body. Then, finally, the Kelvin statement, it says in a cyclic process, it is impossible to completely convert heat into work.
The third law of thermodynamics states that the entropy of a perfect crystal is zero, and when the temperature of the crystal is equal to absolute zero, 0 Kelvin, the crystal must be perfect, or else there will be some inherent disorder. This is connected to the statement of how thermal energy cannot be spontaneously transferred from a cold to a hot body, but instead will be from a hot to a cold body naturally, which usually mentions what the third law wants to state, that nothing will get to absolute zero or 0 Kelvin. We could also relate this concept to the heat death of the universe, because as the energy is transferred, eventually there will be no useful energy to be taken approach of, and the universe will supposedly stop.
A thermodynamic cycle is a series of thermodynamic processes in which, when all are performed, are able to bring a system back to its original state by varying pressure, volume, and temperature of a gas. These processes can also be repeated various times, which is why it is called a cycle. It is important to know that what happens in the thermodynamic cycle is that work and thermal energy are transferred into and out of a gas. The cycle begins at an isothermal expansion, followed by an isovolumetric cooling, and finally it is compressed adiabatically, which causes it to return back to its initial state, and that is the end of one cycle. In a PV diagram of thermodynamic cycle, you're able to find and calculate the work done by the system with the area that is enclosed in the cycle. Being able to create the most useful work in a heat engine is vital in order to be able to have a good engine. To calculate the efficiency of an engine, all you have to do is the efficiency is equal to the useful work done over the energy input. The Carnot cycle is a very famous heat cycle that has the most efficient cycle for a heat engine to use. This cycle contains 4 reversible processes, which are first, isothermal expansion caused by having a system intact with the first heat reservoir, and then adiabatic expansion when the first heat reservoir is at a higher temperature than the second heat reservoir, and then isothermal compression when the system is in contact with the second heat reservoir, and then finally adiabatic compression when the temperature increases from the temperature of the second reservoir back up to the temperature of the first reservoir. The cycle is able to begin at any of these points, but always returns back to the initial state and starting point, since it is a cycle. In the Carnot cycle, you are able to calculate the efficiency of the engine using this formula, which is the efficiency of a Carnot engine equals to 1 minus the cold temperature over the hot temperature. Following the formula, it is apparent that the only way in which the efficiency of an engine is 100% is if T cold is 0 or if T hot is infinite, which are not possible, which is why a Carnot engine may never be 100% efficient. But at the same time, no engine using 2 heat reservoirs of the same temperature will ever be more efficient than an engine undergoing the Carnot cycle.